a gradient vector of f always points in the direction of steepest increase. That is, the direction in which our directional derivative would be the most positive. That's the way the gradient points. So to see why that's true, remember a directional derivative is our gradient times a unit vector, dotted with a unit vector. And well, if we consider the geometric form of the dot product, it's the size of the gradient times the size of our unit vector times the cosine of the angle between them. And, well, if we're thinking about the direction, the only thing we get to choose is theta. The unit vector has length 1, and this product is maximized when cosine of theta is maximized. And that is exactly when the angle theta is 0. So when our unit vector and our gradient vector are pointing exactly the same direction. So gradient vector always points in the direction of steepest increase. Let's take a look at this example we saw in a previous video. Remember, g is a function that models a number of pints of ice cream sold by a company if they sell them the pints at price $P and they spend $A on advertising. This tends to work out a little weird just because of the numbers, but the principles are correct. So given the information that we have, we can write down the gradient vector at the point 6, 1000. That is at a point where pints cost $6 and the ad budget is $1,000. And the fact that the gradient points in the direction of steepest increase means that if we wanted to sell more pints, we could talk about a ratio of decreasing the price and increasing the ad budget. And, well, I don't want to say we can decrease the price by $300. That doesn't really make sense. But think about the ratio. We could say that for every $1 reduction in price, we might increase the ad budget by 1 over $600. So that's not saying much. It's kind of a strange thing to say, 1 over $600. But really what this is saying is that if we wanted to see the steepest increase in selling pints, we should lower the price. That spending money on ads is not the place to find these gains. The second geometric property of the gradient is to talk about its length. Specifically, the length of a gradient vector is the size of an increase in that direction. So remember, the gradient vector points in the direction of steepest increase. Its length is the magnitude of that change, or in other words, the size of the directional derivative in that direction. So let's go back to our example, this function 6 minus x squared minus 3y squared. From the point 1, 2, the gradient, we can check, has a magnitude of square root of 148. So, according to what I just said, the directional derivative in the direction of the gradient should be square root of 148. So the slope we would experience walking in that direction should be this number, root 148. Let's check that that's true. So we need a unit vector. That is, we'll take this gradient vector and we'll scale it by its size. Well, we just found that. And then to find the directional derivative, we dot our gradient vector with the unit vector of the direction. We can let that scalar multiple hang out and just apply it to the dot product when we're done, and see that, yes, indeed, the directional derivative in the direction of the gradient vector, root 148. To see the last geometric property of the gradient vectors, let's take a look at this contour plot. So the contours here are for the same function we've looked at, 6 minus x squared minus 3y squared. And all these arrows here are all different gradient vectors. So remember, a gradient vector is defined at a point. So you change the point, you get a different gradient. And the lengths are not correct here. The relative scale between them is right. But for the same reason as above, I couldn't fit the vector all the way into the picture, so they're just drawn to a different scale. But if you notice that all of the vectors seem to point perpendicular to the contour plots, to the contour lines or the level curves, that's not a coincidence. That's a general phenomenon. To see why that's true, go back to something we said very early in the course when we talked about contour plots. If you were to walk along a contour line, you would experience no change in altitude. Well, using more recent terminology, we could say that the directional derivative in the direction of a contour line should be 0. Right? We would see no change in z as we change the position in the domain. But now, bringing it all together, the directional derivative is the gradient dotted a unit vector, a direction. So if that dot product is 0, if the directional derivative is 0, then that means that our gradient vector and the direction of the contour line, contour curve, would have to be perpendicular. And there are some neat applications of this I think we'll see on the homework or in class. Good job.